Okay, so welcome to Induction. This is not in the book, but it is required for the course. So what is induction? So the principle of mathematical induction. Hello, Sir Lix-a-Lot. Okay, so let's let P of x, or rather P of n, since our domain is the positive integers, so be a propositional function. And you'll understand what this means by usage in a moment. Defined on the positive integers, so z plus, meaning the domain are positive integers. Then we can prove the proposition is true by, so we can prove the proposition, or what we can prove that which is proposed is true. Proposition true by, and here is the process of mathematical induction. So number one, the basis step. The basis step is to verify P of 1, or the first term, whether it start at 1 or otherwise, is true. So you have to verify that the first possible input in counting order is true. So number 2, let's see. The second step is the assumption. Assumption. Holy, one day I'll have spell check on my writing. So we assume that P at some integer k is true. So we're assuming it's true. We're not showing that it's true, and that's a k. That doesn't look like a k. Let me write that k a bit better. So we assume that P of k, the proposition evaluated at k, is true. And then the crux will be the inductive step, which is what induction is all about. So the inductive step, there's 3 steps: basis, assumption, inductive. So we show P evaluated at k plus 1 is true, based on our assumption, on the assumption in step 2. Okay, so note. Induction can be thought of as the following. So note. So the process of induction is to show P of 1. And then the next step is to assume P of k. And the final step is to show P of k plus 1. These are the steps of mathematical induction. Show, assume, show. Show 1, assume k, show k k plus 1. Okay, so this is a lot easier said than done, so bear with me. I'm going to go through a lot of examples, and hopefully this will start to stick. So example. So show that the following propositional functions, that the following propositional functions pardon me, propositional functions are true by using mathematical induction, or by using a proof by induction. So we don't need to say the principle of mathematical induction. It is assumed. Okay, so number 1. Now, what do I mean by prepositional function? So look at this. 1 plus 2 plus 3 plus ... plus n is equal to 1/2 n times n plus 1. So notice I don't have f of n or p of n is equal to here, right? That's what we mean by a propositional function. I have what looks like one function on the left and another function on the right. So basically 2 propositions. I propose that the left-hand side is equal to the right-hand side. Okay, so let's prove this by mathematical induction. So step 1, show, and this is, sorry, for all n positive integers n. So show that, show p of 1. So what is p of 1? P of 1 is going to be 1. That's where I stop because that's n. Is that equal to question mark? Uh, 1/2 of 1 times the quantity 1 plus 1. Well, that's 1/2 times 2, which is 1. Yes, it is. Check mark. So let me do the check mark in pink. Okay, so step 2 will be assume p of some integer k. So what that assumption means is that we're assuming that 1 plus 2 plus 3 plus ... plus k, we're going only up to the integer k, is 1/2 integer k times integer k plus 1. That's my assumption step, which is basically just rewriting the proposition without n's, but instead with k's. And now the, I know, kitty, induction step. It Sir Licks a lot, I know. Okay, so the induction step is as follows. So show p of k plus 1 based on our assumption. Okay, so 1 plus 2 plus 3 plus ... plus not only k, but the next step, k plus 1. So what is that equal to? Well, I claim that, what color should I use? Oops. The first k of these is 1/2 k times k plus 1, to which I'm adding the final k plus 1. And actually, let me move this down. I don't have enough room. And this is by assumption. So we assumed that the first k terms was equal to 1/2 k times k plus 1. So the pink is by assumption. Okay, so let's look at this. What do we have? Looks like I have a k plus 1 common to both terms. So let's go ahead and factor that out. So I'll have a k plus 1. Don't know if that'll help, but let's see. When I factor that out, From the first term, I'm left with 1/2 k, and from the second term, I'm just left with 1. Okay, well, let's go ahead and factor a 1/2 now from each term. So when I do that, I'll bring a 1/2 out in front. Let's do that maybe in blue. Then I'll have my k plus 1. And when I factor 1/2 here, I'll get k plus 2, because I multiply by the reciprocal when I divide out, right? Okay, that's okay. So now we're going to get 1/2 times k plus 1 times the quantity. Well, k plus 2 I can't claim is k plus 1 plus 1, right? Now that's actually the form I need. Do you agree that n in this case was k plus 1? So I needed 1/2 n times the quantity n plus 1, where n in this case is k plus 1. Once I've shown that, I'm done. Check mark. Actually, let me do that in orange. So check mark. So therefore, we found that, what color should I use? 1 plus 2 plus 3 plus ... plus n is equal to 1/2 n times n plus 1 by induction. Okay, so that is our first proof by mathematical induction. So let's do a second one, number 2. So now we have the propositional phrase 1 plus 2 to the first plus 2 to the second plus ... plus 2 to the, let's do nth minus first, is equal to 2 to the n minus 1. Okay, so step 1 is to show that p of 1 holds. So what is p of 1? Well, we're going to the 1 minus 1, which would be 0. So 1, is that equal to question mark? Is that equal to 2 to the 1 minus 1, which is 2 minus 1, which is 1? Yes, it is. Check mark. So the first step holds. Step 2, assume that p at any integer k holds. So that means we have that 1 plus 2 to the first plus 2 to the second plus ... plus 2 to the k minus 1 is equal to 2 to the k quantity minus 1. Okay, and now we're going to show, this is the induction step, so show that p of k plus 1 is true based on my assumption. Okay, so we have 1. Actually, do you know what? I'm maybe going to go down the line. Okay, so we have 1 plus 2 to the first plus 2 to the second plus ... plus 2 to the k minus first plus 2 to the k plus first minus first. Okay, well, what do I know about the first k terms by my assumption step? Oops, wrong color. I know that this was equal to 2 to the k minus 1, to which we're adding 2 to the, well, the 1's sum to 0, so to which we're adding effectively 2 to the k, and that pink was by the assumption step, right? And I don't have enough room. Let me move this a bit to the left. So by assumption. Okay. Okay, so how many 2 to the k's do I have here? If I add them up, I claim I have 2 to the k's here. Minus 1. Okay. So that's 2 to the first. So I claim that this will be 2 to the k plus 1. minus 1, and guess what? Do I have a k plus 1 minus 1 where the n should go? I do. So check mark. So therefore, 1 plus 2 to the first plus 2 squared plus dot 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 plus 2 to the n is indeed equal to 2 to the, sorry, that was n minus 1, that should be there in the exponent. N minus 1 is equal to 2 to the n quantity minus 1 by induction. We've shown it's true by induction. Okay, let's do another. I know that these are difficult at first, that's why we just have to keep on doing more and more and more. So number 3. This propositional phrase states that 1 plus 3 plus 5 plus dot 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 plus quantity 2n minus 1 is equal to n squared. Okay, let's show true for p at 1. Okay, so twice 1 minus 1. So 2 minus 1 is 1. So I just get, is 1 question mark equal to 1 squared? Well, 1 squared is 1. So yes, it is. It works for just 1. So assume true. So assume that p of k is true. What that means is we're going to assume that the sum of all odd numbers until I get to 2k minus 1 is k squared. So now I need to show that p at k plus 1 is true based on that assumption. So what is p of k plus 1? That would be 1 plus 3 plus 5 plus dot 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 plus 2k minus 1, and then I'm going to add to that twice the quantity k plus 1 minus 1. Well, I claim these first k terms are equal to k squared by assumption, to which we're adding. If I distribute, 2k plus 2 minus 1 is 2k plus 1. Agreed? And that step was by assumption. But I really don't have enough room here. So, by assumption. Okay. So let's go ahead and move this down a bit to the left here. So this is going to be equal to, oops. So this is going to be equal to k squared plus 2k plus 1, which is actually quantity k plus 1 squared. Look at that. I needed k plus 1 squared. Check mark. We did it. That was pretty quick, wasn't it? So therefore, we can state that the sum of all odd integers up to including 2n minus 1 is just n squared by induction. So this, okay, so let's note something. These have all been equalities. So let's note that we can also use induction to prove. So we can also use mathematical induction to prove propositional inequalities, so that we don't have to have equals. Propositional inequalities. So what do I mean by that? Well, for example, use mathematical induction induction to prove the following. Okay, so number one, let's say, pardon me, that n is strictly less than 2 to the n for all positive integers n. Okay, for all positive integers n. Wow, I'm having issues writing for all today. So for all positive integers n. Okay, so step one is to show that the proposition is true at 1. Okay, so is it true that 1 is less than 2 to the 1, question mark? Well, what is 2 to the 1? 2 to the 1 is 2. So, yes, it's true that 1 is less than 2. I agree. Okay, so number 2 would be the assumption step. So we just assume that the proposition at k is true. So that means we assume that k is strictly less than 2 to the k. And now the inductive step. 2 to the k. Did that erase? It did erase. So the induction step in solid, not dashed. So show p at k plus 1. Okay. So k plus 1. Well, I claim that that's less than 2 to the k. Let me underline this part. 2 to the k plus 1 based on my inductive step, right? Because k is less than 2 to the k by assumption. But I'd like this to be eventually less than 2 to the k plus 1. Well, is 1 less than 2? Yeah, I claim that this is less than or equal to 2 to the k plus 2. And in fact, it's less than 2 to the k if I wanted to be even more precise. So let's underline, what color should I use? Orange, so these two, and this would be because 1 is strictly less than 2 to the k. And there's a reason I specifically chose 2 to the k and not just 2. It's because where I want to go with this. Well, what is 2 to the k plus 2 to the k? Well, I claim that that's 2 to the k's. And that is 2 to the first plus 2 to the k is 2 to the k plus 1. So we have this inequality still from up here, which still holds true. So this implies, no, shoot, come on. So this implies that k plus 1 is indeed less than 2 to the k plus 1, because all of these steps of logical progression were true. Check mark. So therefore, n is less than 2 to the n by induction. There was no sum here, just simply each term. Okay, let's do another one. Number 2. Something similar. How about 2 to the n is strictly less than n factorial, but now we want for all values of n greater than or equal to 4. So now p, the first step, starts at 4, because that's the smallest step, or the place where this inequality starts. So we have to show now p at 4, the first term, is true. So is 2 to the 4th question mark less than 4 factorial? So 2 to the 4th, oh, wrong color. 2 to the 4th is 16. Is that less than 4 factorial is 24. Yes, it is. Check mark. That works. Okay. So now we do our assume that p at some integer k is true. So that means that 2 to the k is strictly less than k factorial. And based on that assumption, we want to show that p, the proposition at k plus 1, is true. Okay, so what is the proposition at k plus 1? Well, that's 2 to the k plus 1. But that I know is 2 times 2 to the k, right? Okay, well that is strictly less than. What do I know about 2 to the k? Well, I know that that's going to be strictly less than 2 times k factorial, and that's by my assumption step, that 2 to the k was less than k factorial. And my goal is to get where? So my goal is to get to k plus 1 factorial, right? Okay, well, how does 2 relate to k plus 1? Well, I claim that 2, so let's underline this in orange, 2 is going to be strictly less than k plus 1, k factorial, and that's for all values of k greater than or equal to 3. But remember, we start at 4, so we're set. Okay, and that is indeed our factorial. This is the k plus 1 factorial I was going for, so check mark. Because now I have a k plus 1 where there should be an n. Okay, so therefore, I claim that 2 to the n is strictly less than n factorial by induction. Okay, so let's do some different types of these. Which one do I want to do? Okay, so for example, did I do 3? No, I didn't do 3, but that's okay. Well, maybe I should do another. Let's do another inequality. So 1, 2, 3. That's very similar. So let's say my propositional phrase is that 3 to the n is strictly less than n factorial for all values of n greater than 6. Okay. Greater than 6 means that my first step should be at 7, because remember, we're dealing with integers as the domain. Okay, so is 3 to the 7th strictly less than 7 factorial? Question mark. Well, what is 3 to the 7th? So 3 to the 7th, I know that 3 to the 6th is 9 cubed, which is 243, times 3 is 729, right? Is that less than question mark? 7 factorial? 7 factorial. So that's going to be 40, let's see, 5 factorial is 120. Then 6 factorial will be 720. So 7 factorial should be 5040. And check mark, it is true, right? Okay, so number 2, we assume that p of k is true. So that is 3 to the k is indeed less than k factorial. And the third step, we show, based on that assumption, that p at k plus 1 is true. So 3 to the k plus 1. Well, I claim that that's 3 times 3 to the k. Well, what do I know about 3 to the k? I know that 3 to the k is strictly less than, this will be 3 times k factorial, and that is by assumption. So my goal is to get to k plus 1 where that 3 is. So is it true that 3 is less than k plus 1 for all values of k strictly greater than 2, right? And in fact, we start at 6, so yeah, it doesn't matter. We're well within that. Well, what is k plus 1 times k factorial? Well, that's just k plus 1 factorial. Okay, so therefore, did I show it? Yeah, so therefore, 3 to the k is indeed less than k factorial by induction. Okay, so that's number 3 on that. So now let's do a different type of example using mathematical induction. So let's recall first. So n divides a if there exists some integer k such that a is equal to k times n. That is, i.e., n is a factor. Of a. Okay, so when we say divides, we mean it's a factor. So for example, so use mathematical induction. To prove, number 1, that 3 divides n cubed plus 2n for all positive integers n. Okay, so step 1, show that the basis step, the proposition at 1 is true. So does 3 question mark divide 1 cubed plus 2 times 1, which is 1 plus 2, which is 3? Yes, it does. 3 goes into 3 one time. So that's true. So number 2, assume p at k is true. So p at k being true means that 3 divides k cubed plus twice k by assumption. And now we need to show that the proposition at k plus 1 is true based on the assumption. Okay, so does 3 question mark divide question mark wrong color. This is now going to be k plus 1 cubed plus twice k plus 1. Well, let's see. What is that equal to? How do I want to do this? So let's note so k plus 1 cubed plus twice k plus 1 is equal to, actually no, do you know what? I don't like that formatting. I'll just keep it the way it was. So does 3 question mark divide Let's expand the binomials. This is going to be k cubed plus 3k squared plus 3k plus 1. And let's distribute plus 2k plus 2. So on the next page, just 3 question mark divide. Let's combine like terms. Let's do k cubed plus 2k as 1. So k cubed plus 2k. And then the remaining terms are 3k squared plus 3k, and 1 plus 2 is 3. So we know that 3 divides k cubed plus 2k by assumption, right? So, but does 3 divide the other term? So does 3 question mark divide? Well, we know it divides k cubed plus 2k. But what's interesting about the other term is I can factor out a 3. What remains will be k squared plus k plus 1. It doesn't matter what remains. It's because of this 3 that it divides both terms. So yes, it does, check mark, because we know that it divides pink by assumption. Okay, so therefore 3 divides n cubed plus 2n by induction. Okay, should we do another one? Yeah, let's do another one. So, number 2, let's say we have 1 plus 3 to the first plus 3 squared plus plus 3 to the n minus 1. I claim that that is 3 to the n minus 1 over 2. But let's show that that's true. So number 1, we want to show that p at 1 is a valid statement. So 1 minus 1 is 0, so I just have the first term 1. Is 1 question mark equal to 3 to the 1 minus 1 over 2, which is 2 over 2, which is 1? Yes, it is. 1 is equal to 1. Check mark. So number 2, we're going to assume that the proposition at k is true for some integer k, namely that 1 plus 3 to the first plus 3 squared plus plus 3 to the k minus first is indeed 3 to the k, from which I'm subtracting 1 all over 2. Based on that assumption, I'm going to show that p at k plus 1 is true. So what is p at k plus 1? So I have 1 plus 3 to the first plus 3 squared plus plus 3 to the k minus 1. And then finally I have 3 to the k plus 1 minus 1. Well, what is that equal to? I claim that the first k terms are 3 to the k minus 1 over 2. Then I have the plus 3 just to the k, because the plus 1 minus 1 goes away, and that is by assumption, the pink part, right? Okay. So I'd like to get a common denominator. So I claim that this will be 3 to the k minus 1 plus 2 times 3 to the k all over 2. So I have 2 3 to the k's plus 1 3 to the k. So I claim in the numerator I have 3 3 to the k's minus 1 all over 2. And in fact, let me just keep these pink so we see where we're getting them. Okay, so, well, that's 3 to the first. So I claim that that's 3 to the k plus 1 minus 1 all over 2. Well, guess what? That's exactly what we needed to show, right? Because we've got a k plus 1 where there was an n. So therefore, I claim that the sum of 1 plus 3 to the first plus 3 to the second plus 3 to the n minus first is indeed 3 to the n minus 1 all over 2 by induction. So these must be done over and over and over again to really understand them. Saying it aloud is not enough. Okay, so I guess that does it. Does that do it? Is that the whole semester there? That's a whole semester. Okay. Enjoy calculus.